We have seen that GNNs work well in practice, for example in the problem of recommendation systems, where it does better than the widespread use of nearest neighbor interpolation. We argued in the introduction that this is because GNNs exploit the underlying data structure and thus generalize well to unseen data with the same structure. But the key question remains, why do they work well? Or, to be more specific, what properties of GNNs help explain their good performance? In this segment, we will formalize this notion of exploiting the data structure in the form of permutation equivariance. At first glance, this property determines that signal processing with GNNs is independent of node labeling. But on a deeper look, we will show that permutation equivariance actually implies that GNNs exploit the internal symmetries of the graph support in order to improve training. The situation is that time convolutions are intuitive, and this helps a lot in using convolutional neural networks and on understanding why they work and what improvements can be made. But graph convolutions are not intuitive, and this complicates our understanding of them and thus curtails our ability to improve them systematically. All we know about GNNs so far is that they rely on local information and they have an efficient implementation, which, in terms of graph signals, means a distributed implementation. But we don't know much else, formally at least. So what we do when intuition fails? Well, when intuition fails, we need to resort to operating from first principles. We need to derive fundamental properties of the architectures that we use to process data. To do this, let's backtrack a little bit first. What do we know about CNNs? We know that CNNs also exploit the local information and have an efficient implementation. Good. But more importantly, we know that they have two fundamental properties, translation equivariance and stability to deformations of the underlying Euclidean domain. And these are the properties that help explain the remarkable performance of CNNs. In a graph signal processing context, translation equivariance is analogous to permutation equivariance, which helps to improve training by exploiting the internal symmetries of the graph. Let's start exploring this property, formally. A permutation P is a binary matrix that satisfies that the sum of its rows and its columns is 1. Since this matrix is binary, this means that we have a single 1 per column and a single 1 per row. Think of it as shuffling the identity matrix so that no row nor column has more than one non-zero entry. Applying the permutation matrix P transpose to a vector X amounts to reordering the entries of the vector, and applying the permutation matrix to another matrix, P transpose S P, amounts to a reordering of the entries of the matrix. It is important to note that the reordering caused by the permutation matrix is correspondent with the linear operation. That is, applying the permuted matrix P transpose S P to the permuted vector P transpose X is the same as applying the original matrix to the original vector first, that is, Sx, and permuting later, that is, multiplying by P transpose. In a graph setting, a permutation amounts to a relabeling of the nodes of the graph. The set of the nodes of a graph is, as any other set, unordered. That is, there is no notion of which is the first or second or third node. They are just nodes. But when we choose a specific shift operator matrix to describe the graph, we are forcing a labeling of the nodes. And this labeling is a consequence of requiring a matrix description to be able to carry out operations. That is, we need the matrix S describing the graph to be able to operate on the vector X that describes the graph signal, but both the shift operator and the signal share a corresponding labeling. However, it is an arbitrary labeling. Therefore, it is sensible to want signal processing algorithms that are independent of this arbitrary labeling. For an operation to be independent to labelings, it has to be permutation equivariant. So let's start by proving that our basic building block operation, that is, the graph convolution, is, in fact, permutation equivariant. Recall that the graph convolution operator is a polynomial on the shift, and that it depends on the filter parameters h, on the shift operator s, and is applied to the input signal x. Here we clearly see that s and x has a fixed labeling, and that this labeling is the same in both s and x for the graph convolution to make sense as in combining neighboring information. the following theorem states that graph convolutions are equivariant to permutations. That is, for a graph with a shift operator s and a permuted version of this shift s hat, and for a graph signal x and its correspondingly permuted counterpart x hat, it holds that the output of a convolution based on the permuted graph s hat acted on the permuted signal x hat is equal to the permutation of the graph convolution based on the original graph s and acting on the original signal x. Of course, this holds as long as the coefficients hk involved in the convolution operation are the same. The proof follows from basic algebra and the properties of the permutation matrix. Now, that was the proof that graph convolutions are permutation equivariant. What about GNNs? Let's start by recalling that to get from a graph convolution to a GNN, we need to apply pointwise nonlinearities to the output of the graph filter and repeat in cascade. We do know that the graph convolution part is permutation equivariance. But we also know that the pointwise operation is, well, pointwise, and thus it does not mix node values, so it is independent of the graph. Therefore, it must be the case that the GNN retains the permutation equivariance property. That is, since the nonlinearity does not depend on the graph, then the GNN inherits the permutation equivariance property from the graph convolution. And this is exactly what this theorem states, that GNNs are equivariant to permutations. More specifically, for a graph with shift operator s and with a permuted shift operator s hat, and for a graph signal x and the same signal correspondingly permuted x hat, it holds that the output of a GNN based on the permuted graph s hat and acting on the permuted signal x hat is equal to the permutation of the output of the GNN based on the original graph s acting on the original signal x. Of course, this holds as long as the filter taps h of each GNN are the same. Essentially, this proves that signal processing with graph neural networks is independent of labeling. But the permutation equivariance property has a more profound implication, and that is that invariance to node relabelings allows GNN to exploit internal symmetries of the graph. What do we mean by exploiting internal symmetries of the graph? Take a look at these two graphs, where the nodes are labeled with a number and the signals identified with a color. We see that both graphs have the same labeling, so for all intents and purposes of the shift operator s, they are the same graph. However, the graph signals on top of them are different. At least, they are different according to the labeling, since different labeled nodes have different colors. However, if we take the signal on the right and rotate it, then we obtain the exact same picture as the one on the left, except for the labeling, of course, which would then be altered. But the labeling is arbitrary, so it shouldn't matter, and thus we should insist that both signals and supports are exactly the same. So, essentially, although they look different, both signals are actually the same. In fact, they are permutations of one another. That is, both signals are counted as different signals, but are topologically the same signal. But thanks to the permutation equivariance, we know that both signals will be processed the same. Thus, permutation equivariance actually means that the GNN can learn about the signal on the right by seeing only the signal on the left. This certainly leads to faster training by leveraging structure to learn multiple scenarios from a single sample. So we see that the equivariance to permutation is more valuable than apparent. As a closing side note, we would like to mention that there are interesting problems, for example, community detection, where the labeling matters, where it actually matters a great deal. In those cases, an architecture that is permutation equivariant will do us no good, since we will be losing key information. In this paper referenced at the bottom of the slide, you can find alternative non-convolutional GNN architectures that do not exhibit the permutation equivariance properties, and thus might come in handy for such scenarios when permutation equivariance is not a good idea.